So I'm here at Stony Brook, and I'm part of the AMO group. I'm the only third edition there. They're pretty nice group doing ultra fast, which is growing crazily. And we have Harold Melcalf, which is one of the founding fathers of laser cooling. He's awesome, he's great, and I'm very happy to discuss with him a lot of physics. And also we have groups doing ultra cool atoms for simulation, quantum simulation, and things like that. But the talk today is about our work in ion neutral systems. So let's start. See if it works. Hopefully it works. No, okay. Come on. Yeah. Okay. Anyway, first the team. Okay. So of course the work that we present here is just it's a team effort. Not only myself. It's a bunch of people behind that help ask questions, answer questions, and all of us we work together as a team, and we are pretty happy. I'm very happy with the people. So we have Miruna Credo, which is a summer student, Kian, master's, he just finished. Shanghai is a PhD student at the Fritz. Marjan is a postdoc, which she was a PhD student of Red's Lab here in the audience, and with Chiwan, he's also a PhD student at the Fritz. So when I moved to the States, no one of my team wanted to move to the States, so they prefer to stay in Europe for personal reasons, not for nothing else, okay? I just want to say, like, now I'm starting the team again. So let's define what is cold chemistry. So this is the typical definition that you can get in many places, books, reviews, and many all of you know, right? So it's any kind of chemical reaction, whatever it is, between 1 Kelvin and 1 millikelvin, okay? Below 1 millikelvin is the ultra-cold regime, and things get a little bit more interesting. So why people look at the cold chemistry? So this is a very nice paper by Roman Krenz, but basically he emphasized the opportunity that brings cold chemistry in terms of controlling reactions to external fields, or how to tune those interactions by the presence of external fields. So basically, the main idea is like we have quantum effects. Those quantum effects, we can use it in our benefit to do whatever we like it. And here's an example from the group of Arevisius from the Weizmann. So this is how they did a reaction between H2 and metastable helium, and they were able to observe shape resonance. And they did it with a cross-beam experiment, which is pretty cool. Like, it's not really cold, but I don't know, 100 millikelvin or so, but they have a very nice sensitivity and they see all kind of resonance, and it's pretty exciting. Another thing about cold chemistry is, of course, my book. I have to advertise that. That's what the publisher told me, right? So here you can find a basically general introduction about cold chemistry for quantum scattering, classical scattering. And also we have some chapters about new physics. I mean, how to use this high-precision spectroscopy and new things that are emerging, how we can use that in the benefit to understand physics, we understand that more. So when we talk about cold chemistry, depending on who is the speaker that you have in front, you can have like two very different setups. Okay, I want to be clear about that. So cold chemistry, as I said before, is just any chemical reaction between 1 Kelvin and 1 millikelvin. However, if you are a molecular beam people, they will look at neutral, and basically they have like cross-beam experiment like this one. They have kind of control, guidance, and things like that. So basically they study reactions with this kind of tools. Then there is a second part of the community, which basically they do kind of a hybrid experiments where they could trap at the same time charged particles and neutral particles. And this is an example. And this is an example taken from the group of Stefan Bilic from Basel. Today, I'm going to talk about the hybrid ion neutral system. So we are going to study chemical reactions between 1 Kelvin and 1 millikelvin, where at least one of the particles is a charged particle. Okay, just to be sure. So this is a hybrid neutral system. Okay, this is kind of funny. This is an experimental movie, indeed. I mean, taken from the experiment, this is a 7 or 8 Ytterbium-174 ions co-trapped with a bunch of lithium atoms. Okay, this is a courtesy from Henry Kitzler from Amsterdam University. Hybrid ion neutral systems are very interesting because they have many applications. You have applications in action spectroscopy. There are several groups that they use.
Sorry, what is it? These are ions.
Yeah, these are ions.
They're not neutral.
Oh, I think that they have also some neutral, but there's no chemical reaction happening, I believe.
No, I mean,
in this case, only neutrals, but they have also trapped in the same experiment lithium.
so these are time-of-flight ions.
Yes. Well, no, this is in situ image.
Okay.
So basically, since they are doing laser cooling,
Yeah.
they can see it.
Sorry, but you've seen the ions.
Yes. So yeah, we see the ions. We don't look at the atoms anymore. So then we have an application like action spectroscopy, for instance. So there are groups like the group of Sandra Brucken or Stefan Slemmer, that British Lab knows pretty well, but basically they come up with techniques like they use a chemical reaction to improve the spectroscopy of something. In particular, they can look at the spectroscopy, rotational spectroscopy of different molecular ions, which are very relevant for astrophysics applications. Then, of course, we have the
Why it is named, sorry,
yeah, please.
why it is named axion spectroscopy? Why?
Because usually when you do a spectroscopy, basically you shoot your laser or whatever, and then you just see the photons coming out, right?
Mhm.
This, you don't do that. You use a reaction. So basically, that's an action, like use a reaction in order to understand the spectroscopy, but you never look at the light. It's like the reaction, but tell you what's going on. And this is pretty efficient. It's very surprising. Then we have, of course, the cold chemistry, which I'm going to talk today, and also, of course, quantum information. I'm pretty sure that after demo, some of you guys talk about, so Benny talks of how ions can help to quantum computers. There's another application. And the last one is many body physics, which people like Hossein here in the audience have been working in terms of pre-burst and things like that. So I'm going to focus today on how these two things, between the many body and the cold chemistry, kind of overlap together. This is an example of the many body, like Hossein knows pretty well, way better than I do, the polaron business, right? So basically, it's kind of a hot topic, basically because polarons are interesting for materials, but materials are pretty messy systems. It's hard to study, hard to isolate. So then we have the ultra cold system, which is clean, controllable, and then we can go there and check the Hamiltonians and understand what's going on. This is an example, I believe, that most interesting papers, or the very first papers of the polaron problem. So what we are going to try to do is, like, what happens if it's still to have a neutral, like this is kind of a neutral impurity over here. What if to have a neutral impurity, you have a charge impurity? What happened there? What we can learn from it. And we are going to have like two different approaches, two different parts of the talk. One is when we have a charge impurity in atomic gas, or when the gas has internal degrees of freedom. Okay, how that change? So let's start with the single ion or charge impurity in a neutral gas. So the name that it takes is called charge polar, not very, very common, right? So from polar to charge polar, not too much imagination on that name. The difference between the normal polar and the charge polar is like the interaction between the neutral and between the charge particle and the neutral is huge. And then you create this kind of blue cloud around the charge, which basically kind of interact with so many atoms that generate all these many body physics that you guys like to study, right? I don't do that. What I do is like study what happened from a few body perspective. In the same way that the ion introduced this kind of huge cloud of interaction, that also means like you can have reactions, okay? And then we look at what kind of reaction can mess up any kind of many body systems or can help to any many body dynamics. One of the things that can happen is three-body recombination. So basically, you have a charge and neutral, you can go and form a molecular ion, and a neutral, or you can have a molecule and an ion, okay? Just for clarity, some people in chemistry, this reaction is called three-body recombination, it's called ternary association. Basically, because you have a ternary collision and then you associate two of them into something, a molecule in this case. Okay, just to be general. So now the question is how we do that. Okay, now I tell you that it can happen, so how we treat this process. So this is what we do. First of all, we always look at, in a group, before doing something, we always look at if it's worth it or not to do a quantum mechanical approach, or not. Sometimes it's not. And here's what we do. So basically, guys, like when you have any kind of long-range interaction, in the case of a charge neutral, will be like 1 over r to the 4, right? In the case of van der Waals, 1 over r to the 6. At the end, you also have to add the centrifugal barrier, which gives rise to this kind of behavior. So you can always calculate how many partial waves you need to include in order that this guy really hits the collision energy that you are aiming to. You can do that. And the result is this, okay? Whatever, it's easy to derive. So basically, you can always calculate how many partial waves you need for a given collision energy once you know what is your long-range interaction, okay? Once you know that, then you can reverse that. Like you can say, okay, my collision energy is like 1 millikelvin. How many partial waves contribute for a collision of lithium plus lithium, okay? Let's do the experiment. This is what I did here. So here in this axis, we have the collision energy that I am aiming to, and this is just the different examples. So you can see here, if we assume that we can apply classical trajectory calculations or a classical treatment when we have 20, sorry, because this thing is over here. this is supposed to be a 20, right? So I'm going to assume that when I have more than 20 parts away,
You can take that and move it.
yeah,
Wherever you-
okay, like that. So 20 parts away. So then what happened is like if you see, as you expected, already at 10 Kelvin, for instance, is kind of, this is already cold for lithium, sodium. So the heavier you get, the lower you can get the temperature. But if suddenly you make this guy a charge, you can drop the threshold like 1 or even 3 orders of magnitude like here. So basically what it means is like the concept of cold or ultra cold is relative to the interaction of the particles. So you guys are used to neutrals, but when you have a charge, things get a little bit hotter. So basically it means like in all these kind of hybrid traps experiments, where they go to 1 millikelvin, we can use classical trajectory approximations in principle. And now, since now we know how to do classical calculation, how we do it. This is the part that most people have issues, but this is the part I like the most. Okay, it's a pure mathematical approach. So we have a three-body process like this one, right? So there is a correlation. I mean, this is something that you can prove that n particles in a 3D space is equivalent to a single particle in 3n minus 3 space. It's just you basically conserve the number of degrees of freedom of your system. Okay, this is a mathematical entity. So then using that, basically, this is our approach. So we are going to map this problem, which has 6 degrees of freedom. So it will be 9 minus 3 because it's the center of mass motion, goes to a 6-dimensional space. Okay. In the 6-dimensional space, it's easy to define initial momentum and impact parameter. Then by building the vector positioning, where we can go from 6-dimensional space to the typical 3D space, where we can use Jacobi coordinates. We saw Hamilton's equation. We look at the trajectory, and then we go back to our 6-dimensional space. And the reason why we do that is because in the 6-dimensional space, the cross-section has this very simple formula. Really, really simple. So basically, you need to send trajectories, sample in 6-dimensional space, and then count how many of them give rise to the collision that you are looking at, or the product that you're looking at, okay? And this gives rise to this function over here called the opacity, which basically means what is the probability of a reactant for a given input parameter and collision energy. Of course, you notice like here is a virtual form instead of the BDB that you are used for a two-body, just because you are in a three-body world. Okay, so then, please. Sure. This one?
Yes, here. So one thing that I didn't get is we fix the number of partial groups, and then we compute the
Yes. So basically what I did here, like, I'm going to assume that if I have less than 20 partial waves, I should do a full quantum treatment. Okay? And then I ask, what is the lowest collision energy that I need in my system to reach 20 partial waves? And this is these guys over here. For lithium, sodium, potassium, rubidium, cesium. And now I ask the same question, but when the guys are interacting with a charge. And as you see, the guy just dropped. So basically, in other words, it means like from here and on, I can use classical trajectory calculation. From here below, I cannot. Because this is, it means like here, that I will need less than 20 partial waves. And my calculation is going to be meaningful.
It's just the difference between the van der Waals and polarization. Because in the ions, you have the first order is polarization, 1 over to the 4th, and in the neutral is 1 over to the 6th. So effectively, that sort of sets the scale for the temperature you use, whether classical treatment is valid or not. No. Which for the classical, in fact, Langevin equations, which collisions of the pull are valid because Langevin is very straightforward.
Yeah.
Scattering from a polarization and 1 over R to the 4th. And the reason it works for co-collision is because of this.
Basically, with interaction, as José was saying, the interaction is too strong. So basically, if you think in this picture, if it's too strong, you basically you make this guy lower and lower and lower. So they basically you're reducing the barrier and the barrier. So that you need to put more path away for the same energy.
And there's ion and it's 4.
Yes, that makes a big difference. That makes reaction to be faster, more efficient, and the physics a little bit faster when you have a charged particle.
But the value of the n equals 20 is somewhat arbitrary. based on.
No, the tuning is kind of arbitrary based on the following fact. It's like if you do a quantum simulation, I noticed in some of my experience and also looking at some of the work, like when you have more than 10 partial wave, basically you have kind of a bunch of resonance that they overlap, and then there's no way that you can see any meaningful quantum mechanical effect. So between 10 and 20, that is like all the resonance wash out. But when you go to ultra gold, you only have like, I don't know, 4 to 5 partial waves, and then you can see like favorite resonance and everything like that. But you have 20 partial waves, they overlap, and there is just a mess. That's the reason why basically classical mechanics capture the whole behavior, not the resonance, of course. We can never predict any resonance. Okay, is that clear?
Yeah, so in your approach, you want to use a classical. So at the end of the day, like you're not trying to explain basically how it's classical.
Yeah. So what we do is classical. I mean, what we first notice is like we can do classical up to for the experiments, we can simulate everything with classical Frederick calculations.
The temperatures of the experiment?
They can go up to 50 microkelvin, the lowest that they can go. But we have, wait for it.
Okay, one more question.
Please.
But you suffer really for huge three-body recombination, right?
Yeah, that's what I'm calculating.
Okay. So typical lifetimes of these charged polaron are.
Oh, I never look at that.
Okay.
So, but I can tell you what is the lifetime for, I mean, the lifetime for the many body character, I don't have no idea. That's business for Jose, okay? And people like many body people. But not for me, I don't do that. I do few bodies. So then I will tell you what is usually it's like 10 milliseconds. Okay, that's the thing, like, of course, it depends on the density. You make a very huge dense gas, it's not going to be good for you. And I will show you an example where you can really control the nature of the impurity. I will show you. So one sec. Okay, so then we get this. And then finally, just to show you how look like the tritons, okay? That's how we identify three-way recombination. So that you can see here the different distances in different colors. For instance, this is for helium recombination, this is for barium, for rubidium barium plus recombination, and also for rubidium barium plus a different energy. Okay, so rubidium plus and barium plus rubidium. As you can see in all of them, at some point, one of the guys starts to be bound. That means that you have a molecule formation. In this case, a helium 2. This one is a rubidium 2 plus. This one is a barium rubidium plus molecule formation. Okay, this is just to show. So then what we do is we run this for different collision energies, different impact parameters, and then we can transform this into something like that, which gives you the opacity or the probability that I mentioned before, where basically you have the probability as a function of the impact parameter and given collision energy. This in particular is for barium plus rubidium rubidium. So when you have that information, you put it in the equation I showed you before, integrate, you get the cross section. Okay, simple. This is an example. This is the first thing that we did in 2016 in collaboration with the group of Johannes Densler. So they had at that time barium plus single ion in a cloud of rubidium. The rubidium cloud was pretty cold and dense, but not at the VEC level. Okay, it was just at the threshold. Still was a thermal gas. And then they observed that the ion get lost. And they were able to measure the three-way recombination rate that you can see here. So then what we did is like we use our method with little something special, which we didn't notice until it took us some time, is the following. The ion in a pole trap is not in thermal equilibrium. So then it means that when you calculate the rate, you cannot use the Maxwell-Boltzmann distribution. You have to use the real distribution of the ion. How you do that? So then we did a Monte Carlo simulation, that you can see here, for different conditions of the trap, and that's the distribution that we use to convolve the energy-dependent rate to calculate the final rate. Only when we do that is when we get this good agreement. Our calculation is the blue line, and the experimental is the red points. As you can see here for the three-way recombination rate as a function of the excess of micromotion or kinetic energy. You can control experiments. So this was our first good news, let's put it that way.
So what are the different colors in the first plot? The upper.
Yeah, those are different conditions of the trap. So basically, the ion control or initial collision of the ion and things like that.
You can see the green, but the blue and red are more or less will be the same combination.
So yeah, so basically what we notice is like At some point, you can consider it kind of Maxwell-Boltzmann stylish, but overall it's not. Indeed, now we know that this is a Sallis distribution. Sallis distribution. Have you ever heard about that? Sallis, yeah. It's a new, this guy had a super highly cited paper. He came out with a different definition of entropy. And then based on that definition of entropy, he can calculate like a new version of the Maxwell-Boltzmann distribution with a different tail. And that gives you, I mean, that's ready with chaos or something like that. I'm not an expert. But turns out that this, yeah, please.
Take into account micromotion in a way?
Yes. Yeah, here the macromotion is included.
DSA.
He's Greek. Yeah,
Yes,
he's Greek. He's Greek, but living in Brazil.
So where is the Maxwell Boltzmann?
Oh,
No, on this last plot. What would it look like?
over here. Oh, the Maxwell basically we will not get this freckle over here that we see. It will be gone. And also there's a shift.
But what about the other energies?
I don't remember what happened here. I know that when we tried, basically this is the part that we were kind of worried. At least myself, it was shifted, and we didn't know what it was. And I calculate different potential, different everything didn't work. And then one day say, okay, let's do a Monte Carlo simulation. This is a simulation, not experimental results, okay? And then based on that, we put it into the convolution, and then finally we get a decent agreement. So basically, we have a good model for the reaction rate, but we didn't have like the right energy distribution.
Real comparison, that's nice to have the Maxwell Boltzmann there just to sort of show that.
Yeah, maybe a good point. I'm sorry that you were not the referee. Otherwise, I'm pretty sure I should have it. Yeah, that's a good point. Maybe yeah, well, it's already 6 years ago. I don't know if people care about it. So, and this is kind of the lifetime, okay? I told you 10 minutes, but this is assuming a density of 10 to the 14 centimeters cubed. Okay, so this is more or less the scale that you can have in mind.
Sorry, one more question.
Yeah, please,
So
please.
this recombination does depend also on the mass imbalance?
That affects a little bit, but not much.
Okay.
It's not as it's not what you are thinking.
Okay.
It's not like that. We are less sensitive. The thing that matters the most is the polarization of the neutrals.
Right.
If you change the neutral, I think you can change like crazy. But yeah, the mass affects the macromotion. So that's a different thing. I will talk about that.
Does the anisotropy of the polarizability play any role?
We didn't include that with lab. We only include the spherical one. But maybe it does. Maybe it does for the molecular, if you found molecular ion and then in the trap, that maybe it will play a role. And then last year, they keep going the experiment at the next level. And then they knew that you are forming barium rubidium plus, and they wanted to know what happened. Because it was an issue. It's like we knew from theory that we should see barium rubidium plus, but they never saw it in the experiment. Okay? And they didn't know why. So once we asked them, please do the experiment in the dark. The dark means like turn off your dipole trap, because they need a dipole trap to go trap the neutrals, and then you have for the laser cooling stuff or the ion. And then it turns out that if you switch off the dipole trap, then you see the molecular ion. Okay? And then is when they realize, or we realize all together with Olivier Trulias and collaboration, like this is a very messy system. And this is what can happen. So the first thing is like you form molecular ion. Okay? But then the molecular ion can have another collision, do like that, or can have a quenching, or can have dissociation, can have a spin-free transition, can have radiative dissociation, and can have also this process too. All this. On top of that, we have all these lasers going on. And what we know is like this black laser over here. So you create the ions, and the molecular ion over here. This guy dissociates your guy. And that was the reason why we could not see the barium rubidium plus. It's because the light that we were using for cooling the ion and for trapping the atoms destroyed the molecular ions. So basically, we noticed that in order to understand the chemistry of these processes, it's better to be sure like your light is not messing up the product states.
So which photon is it?
Yeah, the black. So the black, this one is the 1064, the typical thing that they use for trapping.
So that's the trap.
Yeah, this one is the trap light. So then basically you form the molecular ions over here, and this guy just go over here. This is it.
To check some states.
This one, this is that happening bounce over here. This will be over here. So you go to the excited state of barium plus and using the ground state. So this is what they observe. And finally, we make like a huge calculation with three-way recombination, the quenching, photoassociation, radioactive association, spin transitions, everything, we'll put it together in a big code.
But could they, is their apparatus is state selective for the ions because they do time of flight, right?
Oh,
Of course, if you do it in a pulse sequence, you should be able to tell the different states they're in, but they cannot, right?
what they do is a little bit more complicated. So basically, if they form a molecular ion, they don't see anything. The only thing that they see in the experiment is the ion. So if the ion reacts, you see a dark. But then what they do, they do mass spectroscopy. Basically, they shake the lattice, sorry, the trap, like given frequency. And then when you inject that guy, you know what is going on. Okay, that's one way. The other way is like you can co-trap your ion with whatever product you have. And then based on what is the frequency of the gas vibrate, you can determine what is the mass of that export.
Yeah, but you cannot, it's not the state selective. You
No.
cannot say that the barium is in a ground state where it's excited 5D.
They know, I mean, we know what is the state
Based
of
on
the
your
atom,
calculation.
but not the state of the molecule. We never know. Because
From
they
here,
can, this guy turns out that this is one of the states that you're using in the laser cooling of the ion. So they can detect guys in the D state. They can detect guys in this state and also in the P state. But not in something higher, we cannot. If there's something above, we cannot. And also we don't know what is the state of this guy. We know from the classical calculation that they're going to be weakly bound, but we don't have an experimental way. Or they don't have implemented anywhere. We don't have a state selective process here. It would be great, but they don't. They have it for the Rubino 3 experiment. They do REMP. But here, I don't know if REMP is so hard.
I mean, there are these people who do these sort of strong field ionization based on the effectively the state of the orbital which the electron is ionized
Yes.
from. They see delay, of course,
Yes.
because they have short pulses. They can tell the difference between
But
nanosecond and 5 nanoseconds. Here, of course, they cannot tell because I mean these things would have delays.
Yes.
The ion you have
the
delays.
thing,
The ion in a 6S and the ion in a 5D
the thing,
will have to be
Yeah.
delayed from each other.
the issue is like these guys are not ultra fast people. Right?
Yeah.
So these guys are atomic physicists and molecular physicists. So now you need to buy, I don't know, a big laser and how much it will cost to put it here. So I don't know if they want to do it.
If they have a tunable laser and just tune it on the ion, you may be able to tell.
Yeah, they tried everything they had at that time. And also they have the REMP scheme for the rubidium 3. I mean, they have another experiment, but it's just 3 rubidium atoms. It's more what he was talking about, like these totality, things like that. And they do REMP. They can do state selective detection. But here, they tried, it didn't work. So that's what I can say. And then I will pass to something that also is kind of relevant. And like if we assume that the equation energy goes like 1r to the 4, it's then you can say like, okay, my maximum impact parameter is going to be of this order, just based on because you assume like a collision happened when the collision energy is similar to the interaction energy. Okay, it's like when the guys can start to be deviated from the rectilinear motion. By doing so, we were able to prove like exactly, I mean, just comparing with numerical calculation, that the cross section for a three-way recombination, it has a power law that goes with energy like this over here. Okay. We went further, and when we went to the temperature dependent rates, and when we compare with a bank,
It's related to which coefficient actually, C coefficient.
yeah, well, that's right. That's right. If you do that with the, I mean, this is kind of the same classical derivation that you did. It's the same business, but for the 1 to the 4. And then what we did is we used that and then put it in the 3-body case and compare with a bunch of different experimental data. So here we have 3-way recombination rates for 2 different temperatures. Sorry, there's not much data for this guy. 78 Kelvin and 300 Kelvin. not too cold, right? And then we have different species: helium, helium plus in helium, neon plus in neon, argon, and so on. The experimental data is the red points, and our predictions is the green points. So this is a prediction just based on threshold law. So no calculation, nothing. Only depends on the atomic properties of, in this case, the rare gas that you have and the mass of the interacting particles. And so basically, what it means at the end, our threshold law, because we're assuming that it's dominated by 1/4, it means like, oh,
Black ones.
yeah, the black one. This was the one paper I found, Russian, of course, 1961 or something like that. He has been the only person I know of that derived the same temperature dependence as we did. He was using a two-step approach. That's another issue. In the sense, like in our calculations, we treat everything like a direct approach. So we have the three guys come together and then see what happens. But what most people do is like kind of the chemical approach. They assume like two guys come first, have a complex, the guy comes in, relax, or destroy. This guy, Smirnov, was the first one that doing this two-step approach got the right temperature independence. This or the guy like this is Dickinson. They were getting something like it's not physically meaningful, but still agree with some data of the experiment. Okay, it's kind of fun. So ours, we know that has been experimentally checked, and also what it means at the end of the day is like if this is true, it means like basically the main channel is this one, not that one. So basically, it means like anytime that you have an ion colliding through recombination with neutrals, you are going to form a molecular ion, not a molecule and an ion. This is something that was hard for us at the beginning, but now I'm totally convinced that's the case. So, and I will show you another case that works like that. Please.
You know which is the reason that the data, I'm actually not sure, but it seems that the data for helium plus, helium and lithium, and data from the one that you computed so between helium plus, helium, and neon plus, neon are equal.
Yeah, they're pretty similar.
And
They're not big, but very similar. This one is like the ratio between the polarizability and the mass.
okay.
It's just a coincidence. Okay, it's not like they have to be equal. They don't have to be equal. Also, even experimentally, you see that it's kind of close, but it's not the same. Okay, there's very small deviation.
Okay.
Yeah, thanks for asking that. By the way, it's a good point you mentioned. So now we go to the second part. Now it's going to be similar business, but now we have molecules as a base. Okay. So a few years ago, we come up with, was the virus hit, and we wanted to have some experimental colleagues, and they asked me, okay, what can we do? What we can explore? I say, well, let's look at the reaction. You have deuterium plus in a bath of lithium 2. And then the funny thing is like, they have that experiment where they have a lithium gas, lithium 6 gas, where basically there is a very broad favorable resonance that they can tune the binding energy of lithium 2. So basically they have a large tunability, and they can create, binding energies, whatever they like it, just by changing the magnetic field. And now the idea is like, okay, now we have a way to control the binding energy of the gas that we are going to have the impurity. How that change the dynamics? And the first thing is like, so I identify what are the reactions that can happen. Okay, there are three reactions. First one is exchange, or what just I learned this morning, like Perez Lab was doing that in his PhD, boron plus H2, right? So this is the same. You have some kind of, you form a molecular charge, a molecular ion, and then one atom goes away. In his case was boron H plus H, right? That was your reaction process. Then we have dissociation, you can break it, the molecule, or you can quench the molecule. That can also happen. Okay, now I have a question for you. What do you think is the most important process of these three? Well, Perez Lab knows, but you should not say, okay, Perez Lab, these guys need to say. What do you think? It's fine, okay? It's just to check intuition. Come on, don't be shy.
C, maybe.
The C, okay? Someone else? See? Yeah, it's called quenching. Jose, are you brave enough?
All of the above.
What?
All of the above.
All of them. Okay. Okay, that's a safe choice. That's a very political correct, it's very correct. Yeah. Okay, so then I will tell you, this is the less important one. That never happened. No, but no worry, there is a reason for that. I'm going to explain. Basically, I know the answer. No, he will know this one is the most important one. The reason why, because the charge always like from something. So it's not good to have a charge never like to be isolated. They would like to react them from something. So basically, I'm going to do about these two processes. This one, we thought that this is going to be important. They would like to be true, but it's not true. Because then it would be nice to cool molecules. But it doesn't work like that. So let's check it out. So what we do, again, we do classical trajectory calculation, but now quasi-classical. So what it means is the following. Like now, so we have a molecule, but we are going to do is we are going to spiral trajectories in a way that the energy of our lithium tube corresponds with the raw vibrational energy that you want to simulate. Okay, how we do that? We use the Bohr-Sommerfeld quantization rule. So basically, you need to sample the phase space in a way that the energy is conserved. And that's how you can go from the continuum of the classical mechanics to the discrete of quantum mechanics. We use model potential for the atom ion, like that, and for the lithium tube, like this one. So we use a typical Lennard-Jones, which that simulates the right scattering length and everything. And this way, this is funny because we don't have any information. No one knows what is the scattering length, so we can pick anything as long as the long range is the physical one. So basically, we know the pulsability of lithium, we know how that interacts. So then we do that. And the good thing is, like, this method allows to include the time dependence on the trap. So far, in the previous calculation I showed you, guys, I didn't include any time dependence. It was just free space, like most of us do, right? But in this model, we can do the time dependence of the trap. Indeed, there are two parts. One is the typical secular, it's called secular approximation, or the secular part of the trap, which is basically our harmonic potential, okay? Time independent. And this is the part that most people hate, but it's always there. I will call the pole trap or the macro motion that Bertha was mentioning. And it is always there. There's no way that you can get rid of it. So then we decide to include it, and then we are going to do two simulations. One with or without. So then we can see finally what is the role of the time dependence of the trap in whatever we are doing, right? So this is the first result we got. So here we have the rate as a function of the binding energy of the lithium tube. Okay, so here's the magnetic field that is best controlled. First, let me show the two main processes. As I say, the C process will not appear. So this is the A process. This is the B process. So we are going to have dissociation, this curve. I'm going to have molecular ion formation. So these two. The first thing that we see is, like, as long as the binding energy of the molecule is larger than the collision energy, basically this guy dominates by far. Super large. But when your binding energy is smaller or lower than the collision energy, then you can dissociate. And then these guys start to grow. Then it's important to notice that all these things always go to a maximum. And this maximum is the Landry-Boone cross-section that Hossein was mentioning. This is the largest cross-section that a system can have. I mean, charge neutral system. And it's based on a adiabatic capture model. You see, this is the roof. But what's interesting is, like, we can see the role of the trap. We can compare the blue with the orange and a given binding binding energy. Then you can see that even can be sensitive up to a factor of 2. So the time dependence of the trap can really change a little bit the dynamics. Of course, if you go to a case where your molecule is super deeply bound, as you can see, there's not much effect. So only when the guys are close, so only when the binding energy of the molecules is close to the energy, is when the trap plays the major role. In other words, if you want to be safe, get far from that region, and then your trap should not mess up your results. Then we did, this is another calculation, but now we are fixing binding energy. Please.
Just to be sure, the time dependence you're referring to is the RF in the,
Yes.
in the pole trap.
Right. That's the macro motion. Yes. Yeah. The thing that everyone hates, even myself. But now I start to like it.
But you can't have ion traps without it.
That's right. Well, now they have this, the group in fiber, they have the optical trap for barium plus.
Yeah,
That's the only one, but that's, it's
but you
the
have to
only one.
somehow compensate for the fact that you have the saddle and the
Yeah, that's,
field.
I think it's a pretty complicated experiment too. So, you know, I will not say much about it. I'm not an expert. So here what we have is now we fix the binding energy of your molecule. Now we change the collision energy. As we expected, lower collision energy, more molecular information. I will put it here. And if you increase the collision energy, you have more dissociation. What you expect, right? More energy you put, the more probability to break the molecule. Nothing interesting. This is another plot where we have a bunch of different combinations between the temperature of the lithium-2, between the temperature of the trap ion and the temperature. Wait, I'm talking about temperature, but I cannot talk about temperature because out of equilibrium, this what it means is average kinetic energy, okay, to be precise. We're using temperature, but it's not, okay? I want to be sure about that. But we can define temperature for the molecular gas, okay? That's totally fine. So these are different combinations. And here is the ratio between the collision energy versus the binding energy. So again, as long as the collision energy is much smaller than the binding energy, molecular ion forms, you win. If you go to the range, when the collision energy is pretty large, when the binding energy, basically, your ion survives, no reaction. Okay? So once we have all that into account, we can come up with this kind of phase diagram. It's not a phase diagram. So basically, like to tell you when your impurity will survive, will not survive. And here is the range of collision energies, where basically your impurity, and like the field, where your impurity is going to die. And
So the magnetic field here refers to the coupling between the charged particle and
the magnetic field here controls the binding energy of the lithium-2 molecule.
I
Only.
see. Thank you.
Okay, so basically what is controlling is like larger, this is larger binding energy, smaller binding energy. And then the thing is like, if you want to do the charge polar business in a molecular gas, then you should go to this regime. Then it means like basically your ion will survive. It's like your ion can collide, but it will break a molecule, but it will not transform into something else. But if you're in this range, then it will go fast.
This is the magnetic, this is for the field.
Yeah, this is the magnetic field for the formation of lithium-2.
So this is the one near the fish pond graph.
That's right.
Control.
Yes, that's right. So this is what it means like deeply bound. This is weakly bound. So what you expect when it's weakly bound, then you break the molecules, everything is simple. And then your charge polar will survive longer, and then you can do all the many-body trick or whatever you want to do. But if you go to this regime, then you should change a little bit and then think that your polar has internal structure. I don't have any idea about how to do that theory. Okay? I'm not a many-body person, but maybe you guys know how to do it.
In order with vibrational states, this corresponds to approximately lithium-2.
Oh, yeah, that will be the binding energy is like 3 gigahertz. That's what I know, and it's a phase-like molecule, so it's pretty like D80 something or something like that. Very high up. So it's very large molecule.
There have been some experiments actually looking at on this in the 1980s.
Cool, nice, interesting. I didn't know that. So you know what is funny that
Looking at later.
yeah. So indeed, that you are saying that is I'm doing all that because we go to the experiment.
Okay, one more question before that. So this phase diagram is independent of the density of the surrounding cloud?
Yes. In this case, I include density. I should have like, you want like a third guy over here, third axis, and then change with the density. So far, I'm just telling you which process can happen. So basically here, independently of the density, you are not going to have three-way recombination unless you go to a huge dimer density. That's a different business. Then you have ion molecule three-way recombination, which is complicated. And in this case, it will happen, but I didn't tell you how fast. Because it depends on the density. In this case, in the experiment, they have very low density gas.
Again, just to understand, so the kinetic energy of the reactor is the kinetic energy of the three particles, or?
Yes. In this case, it's the collision energy between the ion and the molecule. So the molecule is kind of colder than the ion. So basically, you calculate the collision energy in the center of mass of this gas. That's what it is. Okay. Is that clear? Perfect. So then we go to the experiment. Voila. So these guys did the experiment, okay, just to check whether we are crazy or not. So so far we predict that they are going to have molecular ion formation. I promise that it's going to be important. So let's see if it's true. So how they do that in real life? So it's a pretty complex machine. Basically, you have the pole trap. Over here, they have these rods to control and do mass spectroscopy, the phaseoid coils. And then what they do, they have here a ytterbium plus ion, and they have a closed dipole, optical dipole trap, where they form lithium, they trap lithium, and then they move the optical trap in order to be in contact with the ion. Then you look at what is going on. So as I mentioned before, the only thing that they observe is the photons coming from the ion. So you have a laser cooled ion, and then you see kind of bright spot. And in principle, if nothing happens to your ion should be bright all the time. Okay. But then it turns out that when you put in contact your ion with something, the signal looks like this. Sometimes the guy gets dark for a long time. So dark means like you don't see light. Okay, it's like your ion is gone. The thing is like you'll know where it's gone, in the sense like you'll know if it's very hot, for instance, or if it's forming a molecule. You'll know that. You only know that it's gone. And there on the process, like it's dark, and then after some time it gets bright again. So then what it means, like something happened, the guy gets some energy, and then goes back again. So then what they did in the experiment to be sure what's going on is like by changing the power of the optical trap, you can control the density of atoms that you have, right? And they see like the density of atoms go with the power of the trap. And they can look at the charge exchange reaction for the excited state. This is a typical, very well-known charge exchange reaction process. And as you can see, as you expected, it goes linear with the density, right? So more atoms you have, more process you find. But then when they look at the probability of the dark, they observe this. They observe an anti-correlation. So it's weird, right? So you have more atoms, and then you have less. So your ions survive less. So how that can happen? So the thing is like, we know, but then it has to be a correlation with the dimers, not a correlation with the atoms, because we have both atoms and dimers. There's no way that we can separate them. And then what they did is like, they did some mass spectroscopy with different isotopes of ytterbium, 172, 71, 72, 74, 76, I believe. And then they can extrapolate to see how the frequency that they measure, the RF frequency, depends on the mass. And then they see a peak around this frequency that corresponds with a mass of 180, which means like you are forming something with mass 180 is ytterbium plus lithium. So it means like they are really forming ytterbium lithium plus in the experiment. So lithium ytterbium plus is our guy. Okay, so far so good, our operation is going well. So then the operation that I made is like if the binding energy of your molecule is larger than the production energy, which is the case here, then you should have a Langevin rate, okay, which is constant, what Hausen will say. Indeed, when we include that, when we take into account, we have this agreement with experiential data. In this case, in order to get the probability of dark atoms, of dark ions, we fit all these reactants. So we have the universality for lithium, all these reactants for ultraviolet gases, all these breakup channels, we include all of them, and then we can explain all the probability of the dark ion. The probability to find a dark ion, a dark spot in the experiment. The most interesting thing is like now that we confirm that Langevin is the right rate, now we can do the other way around. Since we know how the probability depends on the rate, we can use this technique to calculate what is the density of dimers. And indeed, for our experiment, we saw like the ratio between dimers to atoms is 0.004. So in other words, it seems like a single trap ion can be a very interesting or very efficient detector for molecules. In the sense like it reacts. So basically, when the guy is gone, you know that it's a molecule. And this is a very interesting application. Just as a summary, I would say that I hope to convince you that an ion in a bath, depending if it's molecular or atomic, is pretty reactive. The evolution of a charge impurity can be controlled with external fields in the sense like we have seen like how the pole trap affects the reaction. Also, we can see like some parameters of the condensate matter can be calculated from these principles, but it means like the lifetime of that impurity can be calculated once you know the density, of course. And atomic ions may serve as molecular detectors. But the most important thing is this thing. I would like to consider like few bodies and many bodies should work together for better understanding of science, not just because what is best or whatever. So since it's getting late, I will finish. I mean, this is part of the talk. Then I will talk about other things that we do. But I will show you. No, yeah, just one thing I want to talk, which maybe you like it. Yeah, most people like this. Yeah, I will show this. The dark matter. Okay, we also do dark matter searches, but not with the. I mean, this morning I was talking with Bretislav, and most of the talks that you guys, I know how many of you went to demo about all these precision spectroscopy things. They only use a spectroscopy to find fixed force, dark matter, or whatever, right? How and why they do that? It's just because if you measure something very, very accurate, then you're going to be sensitive to any kind of weird things that you're not accounting for. Okay. However, we have a different way to do things. We can do a direct detection. That's an indirect method. Okay, direct, it means like you have a system made of atoms and molecules that can really react to the presence of something beyond the standard model. This paper, which is pretty interesting. So these guys in this paper, they just come up with different methods or different systems that may be sensitive to this kind of dark matter. Okay, and the idea is the following. We have some kind of dark matter particle. I don't care how they interact. I don't care if it's a mini charge. I don't care if it's an action. I don't care, honestly. What I know is like when this particle interacts with the molecule, it may excite the molecule. Okay? For any kind of interaction, I don't care. And what is interesting is like if you look at the typical energy separation for vibration in molecules, it turns out like you're going to be sensitive to a very interesting mass range between 100 kilotons and 100 megatons. This is indeed a range that people at xenon cannot explore. So this is the range of xenon experiments or high efficiency experiments. So ours will be around here. And this is what we gain. So using molecules, we are going to be sensitive to this range of dark matter. So we can have a direct detection scheme using molecules that can complement the xenon experiment and even extrapolate it. Okay? So how we do that? So this is the idea we have. It's pretty simple. Yeah.
It's an amazing energy range.
Yeah, so 10 to minus 22 eV to 30 solar masses.
Find the dark matter in that range.
Yeah, I know that Jose is not a big fan of that. I know, but what can I say, man? We have to try something, right? So, and just to mention, now you take the picture. So there's only a few models, okay? There's only a few models. There are like more than 200 models. So people come up with different models. I know it's a different business. So high physics is way complicated than AIMO in that sense. And yeah, we're trying to help. And this is our approach. Please. Oh, yeah, I know you mentioned that. I believe that this supermassive black holes theory has been ruled out. Because some people propose like
WIMPs also more or less.
WIMPs. Yeah, this thing supposed to be kind of pretty route. We rule out regions. I'm going to show a picture of that. Because what you rule depends on the mass that you're looking at. You know, because different models have a different sensitivity to a mass range. For instance, if you're doing actions, you are going to be in this range. So if you're using an action model to predict something over here, it's useless. And vice versa, use a WIMP to predict something here, WIMP is not going to help you. Okay, so it can be messy. So anyway, what we do is the following. We are going to assume that we have, I mean, if you have a CO particle, a CO molecule, okay? And then you have it in a very cold environment, cold, say 50 Kelvin. Everything is in raw vibration gun state. You put that gas, you put it underground, you shield it. In principle, you should not get any light, right? That's the dream. But it can really trouble your still can get excited. And then if it gets excited, it will emit photons. And this is our approach. So we can have a tank filled of CO at 50 Kelvin or so. And then depending on there's a collision with CO, they can emit photons that are going to be detected with this photodetector for IR. It's tiny, yeah, but that's not a problem because CO, as I was talking with Betlab this morning, have a very low relaxation time, collision relaxation time. So it's even beneficial. But yeah, CO is not. So it's just to detect photons. And then we have to take care of black body radiation. We can mess up, photon detection. And we have to take care of vibration relaxation, as Jeff Hosing was talking about. How we do that? We need to take care of temperature and density. So if we do 50 Kelvin gas, we're going to get rid of any black body radiation for the same wavelength that this gas is going to emit. And the density, we just need a typical gas density. So we don't need to make it super dense or even non-liquid phase. So only in the gas phase. So by doing that, we get this sensitivity plot, which is what you were asking. Here we have the cross section between anything. I mean, we don't care how they interact, okay? It's like the cross section that you are sensitive to something between something created with the nucleons, okay? That's all. As a function of the mass of dark matter that you are sensitive to with your system. This gray shade area is things that has been constrained or ruled out. So it means like some people did some experiments and they don't find anything. It's gone. However, as you see in this range, where molecules are sensitive, there is nothing open. So if we build that experiment or this setup in principle, we will be able to rule out all these regions over here. And that's the benefit of using molecules. It's just because molecules are very sensitive to this particular mass. And also interesting of using molecules is like in molecules we have different isotopes, right? So then we can be sensitive to spin-dependent interaction models. So if you now change to a different isotope like carbon-13, oxygen-16, now you can be sensitive to any interaction of that matter with the spin of the nucleons. Okay, with our models that work about that.
Now, you're constraining between the blue and the green curve is the region of the masses that you are going to be sensitive.
So we are sensitive between
I just want to understand.
Yeah, sure. This is a fair question. This is typical for any physics, but not for us. So this called a sensitivity curve. Basically tell you what is your sensitivity of the cross section with respect of the mass. So this is the range of mass that we are sensitive to. But as you can see, we are very sensitive to this guy in the sense like we can prove up to 10 to minus 40 centimeter cube I squared, which is very nice. But at this masses, we're not very sensitive. It's just because the kind of interaction we have. So if we build this experiment, which is kind of complicated, we should be able to rule out all these regions, everything. So this gray will be everything like that. If someone built that experiment. Or if you build the green one, it will be this one. Okay, so basically you rule out any cross-section above.
Volume
Yeah.
changing
Yes.
from 20 centimeter to 2 meter.
Yeah, so that's it. So we have, yeah, this is the most complicated part. This is the area of the detector. It turns out to build an IR detection scheme is not trivial at all. Single photon detection for IR is awful. I would like to build that. And there are some technology out there, but to build 1 centimeter square is already quite a lot, a challenge right now. So we assume that in the future, 5 years from now, we can make like 1 meter square. And the volume is the place where you are going to make your CO of 50 Kelvin, which is 2 meters side. It's big, right? And expensive to build a cryostat at 50 Kelvin that can have a 2 meter side cube. Yeah, that's the prediction. And this is kind of a standard in this business, in the sense like people propose. I mean, now there is a lot of interest with graphene, for instance, or some other some semiconductors. So like, you need something that you can control, and in a way that like molecule, right? We know what is the initial state. So anything that deviates from that can be a good dark matter detector. Anything. Also, we look at the spectroscopy of exotic atoms like positronium, we do things like that. But with that, I would like to say thank you for your time, Professors Satterpour and Friedrich, and thanks for the funding, DFG and WO from the Netherlands. Thank you.
Thank you very much.
And WO is
Dutch. Yeah. Yeah. Yeah, it's through my collaborators. So yeah, it's a funny story. I was paid by them the first year.
Thank you very much for this very packed talk. We have some more questions.
I have one question. So we're doing actually a molecular dynamics on clustering of atoms or particles, whatever, different particles, when they're seated with ions. And this is to do with actually toward more exoplanetary atmospheres where you can have hazy environments and you want to get high density, dense aerosols or dense haze environment.
Right.
So with ions, we're doing this and actually we find very interesting features that sort of come up. Now, of course, this is all pairwise interactions.
Yes.
I would like, even before you talk, of course, is to be able to have three-body recombination. So the ion can be combined with to make a molecule. Okay?
Yeah. I see.
Are these things available in a sort of analytical form for the rates?
Yes, for this threshold law, dimension, yeah, it's analytical as an expression and give it to you. You can just plug the temperature there, variability of your
so that we can say that at this sort of densities,
Yes.
there's going to be this rate.
That will work within order of magnitude. Okay, it's not going to be perfect.
That's fine.
I don't know how much accuracy you want.
No, we're not doing super accurate stuff. It's to sort of see, for instance, the morphology of the clusters that form and what densities they have, and so on and so forth.
Yeah, we should talk about that because we are doing that too with DFT.
The DFT.
Yeah, the reason is because in DFT you can include many body effects.
So we've done quantum molecular dynamics, which also involves DFT, but right now, because we're looking at very large systems, hundreds, thousands of atoms, it's more classical.
I see. So you are doing abinitio molecular dynamics.
It's abinitio molecular dynamics. So, okay, so that would be.
At least
is in your paper. So
yeah, but I will give it to you the expression. I mean, it's just
of course,
one
we
line.
need to sort of use the, okay.
So basically, the expression only depends on the mass of the guys that you are taking into account and the possibility of the neutrals.
That's fine.
That's all. So you have that and the temperature.
Some of it in your book also?
Yeah, it's in the book too.
think so, yes.
Yeah, it's in the book. The book I also. So then you can buy it. Well, come on, Jose. You have access to the book, but I will give you the expression. No worries. It's not a problem.
Any more questions?
May I ask? Yeah. So in the first part regarding the charge polar, do you see any back action of the polar onto the cloud? To the dressing cloud?
That's what we are doing right now.
Okay.
Yeah, we are looking at solvation.
Nice.
So I like chemistry, so we are trying to develop a solvation shell model for a charged particle in a neutral path. Because we believe that it's supposed to be similar to what people, I mean, when you dissolve salt in water, right? So we have solvation shell, so it should be similar. So we're looking at that, but of course, this is kind of classical and classical, no full quantum.
Yeah, that's fine. Okay, I have one more question. I mean, okay, if you do this action spectroscopy that you said, normally what I would expect is to see just a single peak, this, which would be the charge polar, right?
So what they do in those experiments are a little bit different. So what they do, for instance, in the case of Sandra Brucken, that she's a collaborator of mine, she has like a 22-pole trap. Okay.
She was a postdoc.
Yeah. So she's now at Nijmegen. So that's the reason why
She was a co.
yeah, she was in Cologne. Now she's a professor in Nijmegen. So what she does is like 22-pole trap. Okay. And then she has like, 100 ions or whatever thing that she wants to study. And then what she does is like she just put helium, like just had like an outlet of helium, put it there, boom. And then she looks at like the mass spectrometer or whatever she forms, right? Like you can have, I don't know, let's say you have CH plus, you're right, and you have CH plus helium, then you have CH plus helium 2. And then she goes and excites CH plus from J0 to G1. And she looks at the depletion of the signal of the reaction. Okay, and then based on that, she can prove exactly what is the energy, is scanning. That's what she does. And also Stefan Lemmer, I believe that they do similar business. This is one of the things that they do. That's called action spectroscopy, but there's other action spectroscopy. For instance, in the freeze, people like Gerd, they do helium tagging. So basically they have something charged, they tag helium or neon, and they do a spectroscopy on that. And then they kind of, detach the thing.
Mass spectroscopy.
Yeah.
So you spectroscopy with molecules, the effects of the photons are like photon
That's what it's called. Like that is some kind of chemical reaction.
action. of photons.
Yeah, it's a fancy name, maybe. I don't know.
And does it make sense to ask, let's say, a question whether I will have an excited charge polaron or a ground ground state charge polaron or something like that?
So the thing is, like, if you're looking at the charge polaron for the few body perspective, like just isolating your ion, most of the time it's going to be, I mean, unless you excite it, it will be ground state.
Okay.
But I don't know if you consider the whole cloud with the many body, maybe there's some kind of phonon coupling weird thing. I don't know what can happen.
Okay. Okay.
That's maybe your business. I don't know how to do that.
Okay, and the final question. Sorry. So, just out of your feeling, do you expect that if you have, let's say, two charged impurities, you will have also induced gravity, right?
Yeah.
And do you expect that this effect will be much more pronounced than the neutral polaron, let's say?
Yes. So one of the things that we are thinking on, like all this bipolaron business, right? So you have two charge, it's going to be way stronger. Just because the polarization length of this guy is like 5,000 volt. So it's almost like the size of your gas.
Yeah, I see.
So you have two, they will interact like crazy. And maybe you can use like the phonons to transfer. I mean, I don't know. I'm not a many body person, but I can tell you that the interaction.
In general, ion seeding of anything accelerate that whatever process that we're looking at. Effectively, ions have a way of just.
Yeah. Ions are extremely
It's
reactive.
like a great attractor.
Yeah.
Mhm.
So we are not looking at, because we are always looking at the few body, right? From a few body, we cannot say much. I mean, we can say that we have two reaction centers, but what is happening with the bath and how they can talk to each other, I think is way more interesting than typical.
We're doing this clustering now with argon.
Mhm.
One of the reasons we chose argon. Important. One reason.
Sure.
Number two is that argon has very small polarizability.
Mhm.
It's tiny. It's about almost the same as hydrogen.
Yes.
Actually, that factor of 3 less. It's like 1.5 for the radioids cube. So whereas hydrogen is 4.5. So this, but the moment we put the ion in, it just
Yes.
because it's polarization potential, it's like it just gathers the whole cloud.
Yeah. It's just.
It's extremely efficient.
The interaction with the second ion would be repulsive.
It would be repulsive, yes, but then you have
Screening.
Screen.
Screening because there is the
Neutral.
medium.
Yeah, that's like what happened in
The
solvation.
Atoms, yeah.
In chemistry, that happens when you make a solution of sugar or salt in water, right? So you have the charge and the negative and the positive in the same thing, and you don't see any electricity, right? But it's just because the guys, the dipole moment, in the case water, forms a cage around that guy to isolate from the other guys. And this is the solvation model. And they have different solvation symmetries, and this is what more or less Hudson is doing, but not with the solvation business. Yeah, and even also interesting that so many way physics can think about it, like what happens when you have an impurity with internal degrees of freedom. I know how they react, I know how fast they can control, but I know how to make the models that you guys come up with. So this is something I didn't see, but maybe you can think about it.
I guess that in the first part we were talking about the bath, which was made of lithium 6 molecules.
Yes.
Right?
Yes.
Is it possible? So my question, I don't know if it makes too much sense, but if you use this, for example, which is the program, and then input some type of statistics.
Yeah, that maybe, but not with our approach because it's classical.
Yeah.
But I know that people like Antonio Negretti and René Gerismo, they are working on that. So they're trying to develop a quantum framework to take into account even all these symmetries, whether you have a boson bath or a fermion bath. I don't know what is the status of that work. I cannot comment much about it. But there is an effect for sure, and then you should be able to see it.
But the molecules would be, we say, totally different. What is the molecule?
Yes.
But so the request of one is bosonic, the other is fermionic.
Mhm.
What difference do you expect?
So-
Make them interact with the ion?
The thing is, like, if you are able to make the ion cold enough, like these guys are pretty close to this wave limit now. They need to go to 10 microkelvin. They're around 50, 70. So they have a new wave that they can go lower. So once they are in this wave regime, then they're going to be sensitive to that still. But right now they are not. So right now they cannot see a difference, but they will at some point. And also the guys at Freiburg, that they have barium plus in the optical trap, maybe they are also sensitive. But the problem is like they are even hotter than these guys. I don't know why. It's supposed to be colder, but they're hotter. They're like 250 microkelvin. Some technical issues.
Benchmark also did some experiments on ions embedded
In the VCs. Yes. In 2010, the first work was with Michael Cole, and he was at Cambridge. He did the first thing, ion in a VC, but they didn't see any kind of many body interesting stuff. Maybe because they didn't have the tools to do it.
I mean, the main problem is micro motion and the ions.
Hmm.
When you bring them together, it's always going to sort of keep you away from the quantum statistics regime. The way, for instance, to do it perhaps would be like what Tim does, which I'm a strong supporter of that. Sort of, you make Rydberg excitation, but you make it so huge that the electron effectively is outside of even the thermal cloud, right, of the VC. Then, but the ion is not free, so it can't just escape because there's no trap for an ion. But it doesn't escape because it's attached to it's still attached to the electron, and therefore he can do a spectroscopy of the ion, and then you can start, because then the ion is auto-cold. It's the same as the DC. Then it will be possible perhaps to look at all the quantum statistic features of the ion and the DC atoms.
Right. Yeah, in a sense that I would say that the atoms.
Now they have an ion microscope, which is really very cool thing. They can make a single ion do a spectroscopy.
The only issue with them of our experiment is like rubidium is very heavy, right?
Yeah.
And
Rubidium,
then
I mean, he doesn't have that
This wave regime is like
flexibility,
at 1 nanokelvin.
but yeah.
He will not get rich. These guys are closer. In the sense, like now they found a way how to modify, how to change the RF potential in a way to even diminish the effect of the macromotion. So, and this system has the largest.
Yes, but getting rid of it.
Rid away, only one guy. The guys at Freiburg,
Yeah.
to be outside, they don't have macromotion. But I don't know why it's so hot. I don't know.
Oh, that I don't know.
I don't know why it's getting like 200 microkelvin.
So the lower temperatures that you can work with this system is how much?
Right now, is this guy has the world record, 50 microkelvin.
Right.
50, maybe 10 at most, if you have a good day. But that's the lowest they can reach right now.
So, sorry, you're going to-
No, I think just.
Just on the final basis. So would you expect that, let's say, if you use like machinery like this hyperspherical formalism would help in these systems?
Oh, we do. Or classical, I didn't say that. Or classical theoretical calculations are hyperspherical coordinates. That helps a lot. But yeah, the only issue with ions is the following. Like when, for instance, like people like Jose Dincao and even Chris, when they do this three-word combination in the quantum regime, they at least know what is the scattering length, right? And then they can, cook some potential with few bound states. But we don't know what is the scattering length of this guy. So I cannot cook any potential that you can trust. So we need some experimentalists to measure the scattering length, and then I can go cook up some kind of model with 2 to 3 bound states, and I can do everything. But right now, for this system at least, I don't have. I can give you any kind of potential, but you will never believe it. That's the issue.
If there are no more questions, let's thank Jesus for a great talk and great.
Thank you, guys.
Thank you.